And there are some attempts to improve the model by considering considering the hardware, specific hardware. And so here we have worked on the model identification, but with a broader application of a general rigid body. So before I continue, I would like to know if the shared slides are, you are able to see the slides well. And
it's good, thank you.
Okay, perfect. Yeah, during my research, I have conducted theoretical and experimental research mainly on 3 topics. One, by proposing a computational framework for identification of attitude dynamics of a rigid body and aerodynamic model of a UAV. And next, by proposing a real-time wind estimation algorithm from the identified model, which is necessary to estimate aerodynamic force and moment to be able to reject them with a controller, to have a precise trajectory tracking or maneuvering. And finally, in the absence of the first 2, I use neural network as an alternative method for the first 2 topics to estimate the aerodynamic force and moment as an external disturbance. Here we review some geometric consideration. Rigid body dynamics is defined on the special Euclidean group, and actually its attitude is defined on the special orthogonal group, or SO3, and its translational dynamics is defined on the Euclidean space. An SO3 consists of 3 by 3 orthonormal matrices with determinant of +1. And there are unique challenges in system identification and estimation for the attitude dynamics of rigid bodies because they are an SO3. And generally, there are 3 main methods to represent attitude. One is using minimal representation methods like Euler angles and using only 3 parameters, but they actually suffer from singularity, so they're not suitable for identification for the attitude dynamics involving large angle rotations. And the other alternative is quaternion with 4 parameter, which is defined on the 3-sphere space. And the problem with this is that, working with sensitivity for system identification. So variation of quaternion are complicated, and usually they are defined in terms of, again, minimal representations for estimation purposes. And the next option is to study attitude directly on SO3, but this actually should be carefully implemented because the numerical trajectories may deviate from SO3 because of the computational error. So here you can see the equation of motion with attitudes represented on SO3. And these equations contain, translational position, translational velocity, attitude, and angular, velocity, and external force and moment to the rigid body. So usually to solve this, we start from an initial state and a general purpose numerical integrators like Runge-Kutta to compute the whole trajectory over time. But this method may result in deviation of rotation matrix from SO3 because SO3 is not closed under addition. And in other words, sum of 2 rotation matrices does not belong to this space. Geometric numerical integration focuses on the numerical integration technique that respect the underlying characteristics of dynamic system. So to solve this issue, we use Lie group variational integrator with an appropriate computational properties. Actually, they are a structure preserving numerical integrator. And among these formulation, I would like to highlight this one. And in this equation, the rotation matrix is updated using a new variable. We show it by F, and we call it relative attitude matrix, which belong to SO3. So using a group operation, it is guaranteed that the updated rotation matrix stays on SO3. So here to present the key idea of the proposed identification method through a concrete but non-trivial example, I explain it for Quadrotor UAV. So we replace the Quadrotor UAV with its mathematical model. Our goal is to have the same output if we give the same input to the model by identifying unknown parameters in the dynamic model. And to do so, we need to define sensitivities in the tangent bundle of configuration manifold. And I have defined a matrix shown by eta here. And this matrix includes information about the direction and angle of rotation that is due to the perturbation. So skipping the details here, we accomplished defining sensitivities on the tangent space. And here we see the computational framework for the identification of the Quadrotor UAV's model parameters. And here the input to the estimated system is actually rotor thrusts. And again, we compute the trajectories and sensitivities of the trajectories to the unknown parameters. And then having the reference trajectory, we compute the necessary conditions for optimality and we repeat this process until those conditions are satisfied. And we use this procedure to estimate Quadrotor parameters. Then having a good identified model, we can estimate wind. So here we see the numerical result, and the initial value for the identification are intentionally chosen such that the initial discrepancies between true and estimated trajectories become large. And here the position and attitude error over iterations are plotted. And we see that initially the error is large, but soon after 9 iterations, we reach an acceptable accuracy. So at this step, we identify the model by estimating the unknown parameters. And on the other hand, having an accurate model is not enough for an accurate trajectory tracking. We need to know the external input or disturbances, which in this case is wind, to be able to compensate wind with the controller. And wind estimation actually is one of the important challenges for aerial robots. And here, computational framework is adjusted and applied for the semi-real-time wind estimation, which you can see the result on the right. So now assume that we neither have a precise mathematical model of wind, nor the wind velocity measurement. So again, flying autonomously in an unknown wind field is challenging, and it is not if it is not a complete failure, right? So instead of traditional control method, we have used artificial neural network here, and proposed a controller capable of compensating unknown disturbances, including aerodynamic force and moments caused by wind. And we have done rigorous, lifetime of analysis on SC3 and showed that the errors are uniformly ultimately bounded. So to take theory into practice, we have built our own UAV, and here we use, brushless DC motors and carbon fiber propellers, electric speed controllers, IMUs, and onboard, computer NVIDIA Jetson, running the Linux operating system, doing all computation for autonomous flight, and information about position and attitude are provided through a motion capture system. This was done indoor. And also we have worked on developing, the flight software and using C++ and, in our lab. So to generate wind inside the lab, we used a pedestal fan with 30 inches propeller, and we have measured the wind speed in front of the fan using an anemometer, and you can see the measurement for about 14 seconds in the E2 direction with the box plot, and the median is shown by red here. So here to show wind effects clearly, we used the same, industrial fan. And in this experiment, 2 autonomous drones are hovering pretty well while restricted to a spherical joint. So they are free to rotate, but cannot move. And when they are hovering, I suddenly turn the fan on, and we see that on the right, drone cannot maintain its attitude and fails, but on the left, the controller with neural network, we do not see any observable change in the performance after we turn the fan on. Okay. So here in this slide, we see autonomous flight of 2 drones that are hovering. Again, here initially there is no disturbance, and I suddenly turn the fan on, and we can see that the Quadrotor with neural network on the top can maintain the desired position and attitude, but the other one struggles. So let's see the video.
I like the noise. Okay, so let's go to the next slide. So now let's see autonomous 360 degrees backflip in front of a fan and a quadrotor here. Actually, a quadrotor is an under-actuated system because there are only 4 thrusts and to control a drone in 6 degrees of freedom. So backflip is not a simple trajectory to follow. And here we did not use neural network, and we can see the drone fails. And however, in the next slide, which we have, the same trajectory and in the same situation, we are using, the adaptive controller to do the 360-degree backflip. And the drone can successfully do that, and I have to say that it's a repeatable, achievement. So not only just one time. So yeah, that actually concludes my presentation. So if there is any question, I would be happy to answer.
Thank you for the interesting talk. Is there any questions from the audience? No, good. Okay, Ed, go ahead.
Yeah, I always have one. I have a comment on you mentioned initially the representation you use and that you chose to have a rotation matrix which you ensure stays into SO3. A couple of years ago in computer vision, they switched to using the 6D representation, where essentially you use the first 2 columns of the rotation matrix. And then because the third one needs to be orthogonal, you can infer that.
And to stay within, to make it a rotation matrix, you would always normalize and make the first two orthogonal. I wonder if that's also used in robotics, because I don't think it's super novel, but it turned out to be very useful for optimizing with neural networks and so on. It simply worked better than having a full rotation or quaternion. So I wonder if there's anything similar and whether you have tried that or.
So here I used, the full matrix. It works, and it was, simple enough. We just wanted to avoid, singularities that Euler angles has, or complexities of quaternions in, defining sensitivities, and it worked. So we didn't try anything else.
Yeah, I just wonder also if you have heard about that, because often these things are reinvented, and often robotics actually before computer vision. But yeah, no, just a comment.
Yeah, okay, thank you.
Okay, Jason?
Oh, that's us here in the viewing room. I'm Steve Waslander. I was just curious, most of your experiments seem to have steady state wind disturbance. Did you look at sort of time varying, like gusting wind?
Yeah, I can show you the plots that we had here. So here I used an anemometer to measure the wind in front of the fan. So the fan do not actually, an industrial fan do not generate a clean wind in front of the fan. So here you can see, for example, during 14 seconds that I keep the anemometer in a specific position exactly in front of the fan. We see the variation of wind, right? And this is the the median of the variation. So it is yeah, it's not, I cannot actually say it's very steady, because yeah.
Okay, thanks.
Thank you.
Samuel?
Yeah, I had a question. For the part of the model that is adaptive over time online, are there ever any issues of some sort of like distributional shift, or like almost like a catastrophic forgetting that might lead to a decrease in performance as the parameters update online? Or is it always typically like stable behavior that you've observed?
I haven't seen any, decreasing behavior. I don't, okay, the trajectory, the trajectories that I chose, so the 360-degree backflip was very short, but there is another trajectory for, maybe a couple of minutes, that the fan is here, the quadrotor flies, from here, comes toward the fan and goes back. And I haven't seen the, the deterioration in performance, during this trajectory, but it wasn't, very long, maybe a couple of minutes, not more than that. I haven't tried that.
Yeah, great, thanks.
Okay, thank you.
Any more questions? Okay, I have a quick question. If we bring your robot to somewhere that the wind constantly changing the directions, like for example in Scotland, the wind coming from all directions and super strong, you think the method will still be able to adjust that?
So for sure, there are different, constraints for a UAV, right? First of all, the amount of thrust that a UAV can generate depends on the hardware, right? So we cannot, say this method works for, the wind, which is, I don't know, maybe 20 meters per second, so it depends to the hardware that we have. Sometimes, the controller wants to, generate more thrust that it's possible with the hardware. So we have, the actuator saturation issue here. So so there are, limitation of based on the size of the quadrotor and the size of rotors that it have and the amount of wind.
Okay, thank you. Ali?
Thank you very much for your presentation. I'm wondering if there is any possibility for adding online training for your neural network when it's flying, when it's on the flying, to improve the performance. Have you?
Yeah. So yes, for sure, having an online training and exposing the UAV to different, maneuvers in different, wind conditions help the model to improve. And when we have a good model, which is, valid in different operating conditions, that should help, right? Yes.
Okay, any more questions? Oh, okay, so let's move on to the oral presentation. So Mahdis, do you want to take over and introduce the speaker?
Yes, sure, I can. Thank you. So we have two presentations here, and one is called ROS-X-Habitat, Bridging the ROS Ecosystem with Embodied AI by Chen, Yang, and Dr. Mitchell. And also the next would be Temporal Convolutions for Multi-Step Quadrotor Motion Prediction by Looper and Dr. Waslander. So I would like to welcome Chen to share the slide and start the presentation.
Yeah, thank you very much for the introduction. I want to double check if you guys can hear me loud and clear.
Yes, that's good.
Okay, awesome. Yeah, I think it says I cannot share my screen right now because another.
Mahdis, I think you need to unshare first. Okay, give it a try.
Yeah, it is working now. Can you guys see the screen? Okay, awesome. Yeah. Again, hi everyone. So I'm Guanxiong Chen from the CS department at the University of British Columbia. So today we're presenting ROS-X-Habitat, bridging the ROS ecosystem with embodied AI. Embodied agents that process visual inputs are useful for a lot of applications, from assisted manufacturing to welfare surveillance. Recent advances in deep neural networks have sparked exploding interest in learning-based agents specifically. These agents, especially the ones trained with RL methods, require simulation offering a high level of photo and physical realism to bridge the sim-to-real gap. Although many platforms exist for training and testing such agents, we're particularly interested in AI Habitat because of its configurable design and, more importantly, its photo and physically realistic simulator. Another line of work we look into is the robotics middleware, specifically ROS, which offers a large arsenal of drivers and utilities to streamline the development and deployment of robotics applications. However, deploying agents trained under Habitat in the real world has not been a walk in the park because the platform did not come with a rich set of drivers and debugging utilities. Although an existing work attempts to bridge the two ecosystems, it does not integrate Habitat's physics-based simulation support and offers little customizability. Without the support of physics, we wouldn't know if Habitat's visual navigation agents trained in a discrete action space can still perform well when running in a continuous action space with real-world dynamics fully simulated.
Another problem. You still have your zoom windows open on the right, so we see a bit of black box.
Oh yeah, sorry.
You can move them, then we see the whole screen.
Is it working better now?
No, it's on the left. I don't know if you can close that entirely.
Yeah, let me see. How about now?
Yeah, not very small. If you put it to the, yeah, now it's gone. Yeah, that's great.
Okay,
that's
awesome. Great. Yeah. So another problem with the the ROS ecosystem is that Gazebo, while being the canonical choice of simulation in the ROS community, lacks the level of speed and photorealism for effective training and testing of learning-based agents. So we aim to develop an interface that bridges the two ecosystems in order to take advantage of the strengths of each. So to address the problems with the existing work, we derived the following requirements for our interface. It should allow both classical and learning-based agents to be tested under Habitat's full physics-based simulation environment while introducing minimum performance impact. It should also streamline the process of debugging learning-based agents and deploying them in the real world. We implemented our interface as a collection of ROS nodes, topics, and services, and exposed them fully to users for customizability. We can run it in any of the three modes of operation. So under mode A, which we refer as the regression test mode, we can run a Habitat agent inside Habitat Sim. We'll explain later how we use this operating mode to evaluate the performance impact of our interface on evaluating agents. And under mode B, we can run a ROS-based planner inside Habitat Sim to take advantage of its photorealism. Under mode C, we can run a Habitat agent inside a ROS bridge simulator, such as Gazebo for debugging. We use this mode to demonstrate that our interface can be easily extended to bridge Habitat agents with other ROS-based utilities, so streamlining their physical deployments become possible. We required our ROS bridge to be able to leverage physics, but not degrading navigation performance too much or introduce unacceptable running time. So we like to ask, if we test a Habitat agent training a non-physics environment under physics, is it still going to work? Is navigation becoming unbearably slow? So we evaluated a pre-trained Habitat RGBD agent on the point-go navigation task using over 1,000 episodes from the Matterport 3D test set. With the SPL metric under two configurations, discrete actions, time step by a non-physics-based simulation engine, or continuous actions time step by the physics-based bullet engine. We did the evaluation entirely under the Habitat framework without the ROS bridge. Under the second configuration, we first map each discrete action, for example, move forward by 0.25 meters to a sequence of velocities. Then at each time step, instead of teleporting the agent from one state to another, we simulate a non-ideal actuation, taking account of dynamics such as friction and interaction with the other objects. Also under physics-based simulation, we simulate the fine geometry of an agent. We noticed that metric drops slightly from 0.495 to 0.455 after we introduce action mapping and non-ideal actuation. Looking into the failed cases, we see that after turning on physics, the agents can no longer penetrate a wall or climb upstairs. Runtime-wise, we noticed that the time to evaluate the entire test set increased significantly, but the modest performance drop in navigation confirms that because a discrete agent can still perform fairly well when simulated with physics, we can effectively mitigate the runtime impact by only turning on physics during validation or testing. And another question we want to ask ourselves is, after placing the agent and the simulator inside ROS nodes, does navigation performance stay the same? And is runtime still reasonable? So we evaluate the test set, both with and without the interface. And in each case, we tried discrete as well as physics-based simulation. So we found that after introducing the ROS bridge, navigation performance is nearly identical, and runtime overhead due to ROS communication is still acceptable because we can achieve real-time performance. Also under mode B, our interface allows users to plug a classical ROS planner into Habitat Sim to take advantage of its physics-based photorealistic simulation. And here we mapped scenes from the Matterport 3D test set, attached the local bot model to our agent, and constructed two navigation episodes for the move-based planner to navigate. And under mode C, we show that another use case where users can plug a Habitat agent into Gazebo for the purpose of debugging. Moreover, we use this case to demonstrate that it's possible to bridge a Habitat agent with hardware utilities under ROS. So in conclusion, our ROS bridge makes the following contributions to the community. So it grants Habitat agents access to ROS utilities, but also allows ROS-based planners to operate within the physics and a photorealistic Habitat sim. The extensible design allows community members to make further contributions. In the future, we plan to integrate Habitat agents trained for more tasks, develop more tools for testing classical planners in Habitat, and also implement a physical deployment pipeline. Yeah, thank you guys for watching the presentation. And do you guys have any questions?
Okay, thank you very much. So we would like to have the questions after the second talk. So now I would like to invite the second speaker to share the screen and present their work. And after that, we will have all the questions and answers.
Hello, everybody. Can everyone hear me okay?
Yes.
Excellent. And everyone can see my screen?
Yes.
Great. So welcome, everybody. My name is Samuel Luber, and I'm here to present my work with Professor Stephen Waslander at the University of Toronto Robotics and AI Lab on temporal convolutions for multi-step quadrotor motion prediction. So our goal for this project was to facilitate drone autonomy by improving the capacity of systems to model future motions. So there's two main applications for this in a typical navigation pipeline. There's control methods, which operate at short timescales and require high accuracy for future predictions. And there are planning methods, which operate at longer timescales and have relaxed accuracy requirements. So for both of these use cases, we first consider a dynamical systems model of the quadrotor motion, which is typically what's used for either planning or control. A standard model of the quadrotor dynamics is built from the basic equations of motion, as we show right here. So, this is pretty simple in theory, but in practice, you can see how this might become a challenging system to model. Firstly, the robot operates in 6 degrees of freedom space, but only has 4 actuated degrees of freedom, meaning that it's under-actuated and has non-holonomic constraints. These constraints lead to the position dynamics being tightly coupled with nonlinear rotational dynamics. In addition, complex actuator dynamics and aerodynamics are represented by these simple linear and quadratic models, which you can see in the equations for motor thrust and for the linear velocity kinematics, which don't fully capture the effect of these disturbances on the system. And so a lot of work in research has been done on properly characterizing these systems to build accurate dynamical models. So other works use empirical methods or use basic system identification to try and get the value of specific parameters under specific flight modes and for specific aircraft. However, this ends up requiring a lot of effort, and the resulting models typically work over smaller time horizons, after which state disturbances and unmodeled phenomena typically dominate. And so as an alternative, we've decided to reframe this problem in a model agnostic way that might be a little bit more familiar to those in the machine learning community. We simply try and predict a future quadrotor state given a series of past states and a series of control inputs. In essence, this is a time series predictive modeling problem. One important feature is that by using a history of previous states, our quadrotor state no longer has to be fully Markovian and include all of our system dynamics, but rather these more complex dynamics only need to be partially observable in our data for us to make meaningful predictions. So once we set it up in this manner, we can then leverage any standard learning-based sequence modeling methods, which have gotten better and better as the state of the art has advanced over recent years. However, one extra key difference is that our future predictions are conditioned on our control input, which is kind of the fundamental issue with control systems. So the way that we address this in our research is very simple. We augment our state with the control inputs and provide our model with both a past state matrix and a future state matrix that has the control input but that masks the kinematic state. Once we frame the problem this way, we can look at various methods of modeling sequences. When it comes to quadrotors, Multi-layer perceptrons and recurrent neural networks have been used for tasks like these, but new architectures are emerging in other fields that provide some significant benefits for modeling dynamical systems. And so in our work, we studied the application of temporal convolutional networks for a quadrotor motion prediction tasks. Temporal convolutions make slight modifications to existing dilations or dilated convolutions, and provide us with an architecture that is very well suited for operating over one-dimensional time series. With this specific configuration for our convolutions, we can predict a large number of future states in a single forward pass. And this is highly parallelized and can be done very efficiently. As in prior works, we can stack these temporal convolution layers one on top of the other to create deep TCN models. And so our architecture is presented here. In our paper, we've run several ablations on some of the key parameters for these types of models. And so what you see here is basically the best performing model under our experiments. We also studied TCNs. Beyond this like fully convolutional architecture, we also studied TCNs within hybrid models, where we combine TCN components with our dynamic systems model from the previous slides in a fully differential equation solver. We tried 3 different configurations for this based off of previous works. The first of these attempts to learn the motor dynamics using a TCN component. And so you can see here that the TCN predicts motor thrusts, which it then feeds the physics model. We have another configuration here where the TCN learns essentially a residual term on top of the physics-based model, which you can think of as all the unmodeled aerodynamics and other effects that might not be considered. And then lastly, we can combine both of these approaches. Overall, we see that these types of TCN hybrids do provide a slight improvement over physics-based models or the state-of-the-art in RNN LSTM hybrids over longer time periods, which is interesting. However, the most important finding that we see is that actually the fully convolutional TCN network is the one that performs the best, especially at longer time horizons, but pretty much across the board compared to any of the hybrids. What we believe is that these models are more expressive and better able to learn the highly nonlinear aerodynamics that are required to make these types of predictions. You can see here some plots of our predicted dynamics versus the actual flight paths that it's tested on. And you can see here that things track relatively well. Once we established this, we also performed an analysis on model scale, where we found that the performance plateaus at a certain model scale, which is an interesting thing to think of. Here, the scale, which is a function of the number of layers that we added to our network, and ultimately the number of parameters. However, at a certain level, adding more parameters doesn't improve performance. We believe that now data becomes the most important bottleneck in our model's performance. We can look at this further by diving into the histograms of the errors within a network across time. And we can see that most timestamps, or the predictions at most moments in time, have a long tail of errors. These are pictured here. So you can see that the errors are, or the performance is significantly reduced. These are all outlier samples, which have either very large pitch and roll values, or very large velocities, or large control inputs. And ultimately what these represent are the tail ends of our distribution when it comes to all of these different state variables. And so ultimately what appears to be happening is that the samples that are least often found in our data set, which was taken at hover and typically has very low pitch and roll, low velocity, and low control inputs. So the samples that are seen less often are the ones that ultimately have the worst model performance. What this might suggest is, for our modeling, is that moving towards a learning-based approach basically allows us to shift our focus from modeling rather to curating large and representative data sets, which will ultimately help us secure more robust performance gains and also see the types of improvements that we've demonstrated for temporal convolutions. So yeah, that's the presentation. Thank you so much for listening, and obviously I'll be available for questions.
Okay, thank you very much. So now it's time for question and answer from the two speakers that we have. So if there is any question, please simply unmute and ask, please. Okay, or maybe if you feel comfortable, you can write the questions in the chat. So I have also a question. Okay, we see a question from Jason.
All right, so this is from the viewing room. Hello, yeah, I'm Adam. This is for the first presentation. First of all, so I like to see these sort of software infrastructure projects. I think that's really cool and useful for everyone. I was wondering if you've done any testing on whether adding ROS to the mix adds any additional sort of variability or sort of difficult to predict or noise in your simulations just because of the inter-process communication and the nature of ROS's message passing. Like, would that be sort of a problem, especially for learning-based approaches where you might want something a bit more deterministic, or not an issue?
Yeah, that's actually a pretty good question. We actually wrestled with that quite a bit during our testing. So we actually confirmed that adding the ROS middleware between the agent and the simulator actually it doesn't change the navigation performance. So we actually manually inspected a couple of navigation episodes, and we found that the in terms of the number of steps taken by the agent to reach the goal from the initial position, and also the metrics, like they are all pretty much the same, and the errors are only within the floating point round off margins.
Okay, all right, yeah, no, that's good to hear, because I mean, especially I guess in the learning community, ROS has a bad reputation for like various reasons. This just might be one of them, which is maybe not as important as you find out. So thank you very much.
I see.
Okay, so
I have a question for Sam. So remember in your results table, I see that the TCN based method works longer for like a longer horizon. And I remember there's a table where you show that for the T 0.01 second, the physics based method works better. Just wondering if you have any comments on that.
Yeah, I mean, I think this tracks with our intuition about how these systems evolve, because the shorter the time horizon, the more that the system basically resembles a linear system. And so the physics-based system probably just does a better job of propagating forward very simple linear dynamics to within like higher floating point accuracy, I guess. But it's really in the longer time horizons that you'll see more significant and difficult to model aerodynamic effects. And that's typically where like a learning-based system will perform a lot better.
I see. All right, thanks.
okay, thank you. So maybe I can ask a question from Sam. So I saw that you have used the neural network to predict the state of the quadrotor as well, and I think you also used the rotation matrix. You flattened the rotation matrix elements and added to the position and velocity to make the state vector. I'm not sure if this is correct or not, but you can correct me. So if you have used, the neural network to predict the state and to predict the rotation matrix, which is among the states, then what did you use to keep the rotation matrix as a rotation matrix, to keep the orthogonal properties of the rotation matrix? Have you used any constraints? Because otherwise, I think if you continue to do prediction, then rotation matrix will not keep its property, and it will deviate from SO3. So,
yeah, that's a really good question. In the state representation that we use, we actually only use Euler angles as the rotation representation. So it doesn't have as many constraints as the 9-value rotation matrix. But like this is still, I think, a little bit of an area for improvement when it comes to implementation, because I feel like if this is a parameter that you're trying to learn, I don't think that it varies smoothly, right? Like there's certain properties about Euler angles that make it pretty difficult to learn. But it's a pretty commonly used, I guess, first attempt at modeling orientation dynamics.
Yeah. Okay, thank you. So I see that there is another question.
Okay. Yeah, so I have a question for Sam. I can see in your work, probably there is a margin for error when it's actually applied to the real world problem, but there are some out of distribution, probably data points that it's very important to handle them. So I was wondering, have you measured how your model performs versus the physics-based modeling for kind of out of distribution, noisy samples or situations?
Yeah, so like as I was alluding to in the last slides of the presentation, the more that a given flight sample is outside, let's say, the distribution of data that it's trained on, the more the performance degrades. And we see that pretty significantly, which is why most of our models have this like long tail of errors. And so this is actually just on data that is taken from the same quadrotor in the same flight conditions. And so you can see that without any additional retraining, obviously the model performance would be very poor. However, there are benefits, I think, to this kind of data-centered approach to modeling dynamical systems like these, because there are methods of applying transfer learning or simply of improving your data set that will make your model more generalizable, or simply be able to transfer some model learned on a given distribution to another. And that might end up being a much simpler and easy to implement solution than the work necessary to transfer physics-based models from a certain, let's say, flight regime to another, right? Because these are problems that occur in both methods. If you're modeling a system based on data that's taken in one regime and you take it, try and model another regime, you're generally going to get bad results. And so I think if you look at this from a data perspective, then this challenge becomes a little bit more tractable, I think.
Okay, makes sense. Thanks.
Am I next? I'm not from robotics, so I wonder how long it takes to implement the system, maybe to both or even all three speakers. Particularly if you're working with real robots, I can imagine there's much more time you spend in implementing and getting it actually run on these systems. So the projects you presented, are these half-year projects or 3-year projects or 10-year projects? Let me know.
Maybe I can get started. So for me, like the majority of this work is done over the course of about 4 months as a summer USRE project. But there was some prior work done by another summer student in the previous year.
I see.
Yeah, I mean, I guess for me, this initial work started as my bachelor's thesis at University of Toronto, and then obviously took a little bit more extra work to get it into to get some final results on it. And yeah, I mean, like obviously, I think there's a lot of extra work that would be good to do before like these things are deployed onto systems. I think these types of models that I presented have some applications in planning, for instance. So I think working on systems that would be able to integrate like neural network predictions for simulating dynamics for planning purposes. Who knows? That could probably take, that'd be probably a separate project on itself.
And I
but
guess
yeah,
you can also
my own
build upon rich frameworks developed in the lab or in the community.
Yeah, of course, right. And I use existing data sets, which I think is a really big thing. I think collecting your own data for any type of machine learning done on robotics can be difficult sometimes.
Thanks.
Okay, thank you. So any other question? Yeah, maybe I ask a very, very general question. For those students who are new to robotics and would like to learn, start doing, simulation on robotics, and they have, topics like ROS, OpenAI, GEM, and I don't know, Gazebo and AI Habitat that is used here in this presentation. So how a student should know which one they should start first, they should use first, and how these relates to each other actually. So maybe the question for Guanxiong.
Yeah, I would say probably in terms of like messing around with the simulation, I think that's usually the kind of like the entry point for most of the new people into the field. But then like as you kind of like as your skill set progresses, you kind of want to start to mess around with the hardware. But actually, I don't have much experience with that because essentially like during 2020, after the pandemic started, most of the labs were shut down, and we don't really have much access to the physical hardware. But I would say maybe the easiest entry point is to start off with the some kind of like a popular open source platforms like ROS or ROS2. So that's really the easiest pathway, like starting point for most students, like when they were like in undergrad.
Okay, thank you. So we still have a couple of minutes left.
Yeah, but that's fine. We don't have to force it if there's no question. We had a great discussion.
Okay.
We only had two presentations in this session. Otherwise, it was an odd split. So
yeah. Yes, we had very good presentations and very good question and answers. So I would like to thank again the two presenters with their very interesting talks and research that they presented. And if there is no other question, we can end the session now. So
yeah, let's thank everyone.
Thank you.
We thank Mahdis for giving us a talk and then help out organizing the section. Thank you.
Okay, thank you very much, everyone.
Yeah,
Okay.
the next thing coming up is the poster session, I guess, and coffee break. So we thought in the Zoom, it's really hard to talk to each other because you talk to everyone and maybe that's not what you want. So you could already join this Gather Town platform. I'm not sure if you've checked it out yet. If not, check it out. It's like a little 2D game where you run around with your character and you can speak to the people close by. And there are also these private places. Maybe I just share how it looks like if you haven't seen it yet. So follow the link I just put in chat. Then you should have a similar view as me. Can you see my screen now?
Yeah.
Excellent. Yeah, so you should spawn somewhere randomly in this room and can walk around. I see Mohammed is here. So currently I would only speak to people in the neighborhood of me, but then if I go to a poster, I would talk to the person there and only the persons next to the poster could hear me. And the same here with these colorful areas here. We're going to use that for the social event. If you want to talk just to a particular person and you want to know to whom you're talking, because as in the real world, it's not quite clear how far your reach is, otherwise in this virtual world. But as soon as you enter one of these private spaces, you just talk to the people there. So that's good. If you want to catch up with somebody, then yeah, just move together in one of these rooms. You can also click on persons, like if I want to move to Eric, I could follow him. If you want to walk around together in these poster sessions, you're not going to get rid of me now anymore. So yeah, check it out because that's where we're going to have the poster session. So we expect presenters to be next to the poster, presenting the poster. With X, you can open the poster, have a close look with them. I think the presenter can even point as well. So yeah, you can have a discussion about parts of the poster. And yeah, that's what's going to happen at 12:45, I guess, in 15 minutes. But yeah, feel free to use it already for a coffee break. Have a little chat. I'm happy to chat with anybody who is around. I will hang out here for the next few minutes until it starts. And reach out to me, particularly if you have trouble opening that. So Chrome is best. A recent version of Chrome, Firefox, I think, works as well. Internet Explorer, or how is it called these days, should work as well. So all the modern browsers should work. The best thing is if you want to switch, first turn off your camera in Zoom, because only one program can get hold of your camera at the time. So turn off your camera in Zoom, then join the space, and of course give the browser access to your camera and microphone. Otherwise, you will not be able to talk to others. There's also normal chat functionality. If you want to provide some additional material next to your poster, that's possible as well. Yeah, so that's a quick run through this GatherTown platform, and we do have the sponsors present here as well. So maybe not all of them will be present, but you can check out the poster and then go to the link if you want to know more. Look up the webpage.